Circle math. All right, we are back for our study guide, semester 2, questions 11 through 20. So in this one here, this number 11, we're comparing two different functions, and these functions are exponential. This is exponential, and this function is also exponential. And what we need to do is compare the two. So as you can see, they have the same domain, the same range, and the same asymptote. They do not have the same y-intercept. And the reason that we know this is two different reasons. Overall, in general, exponential functions kind of look like this. They have the curve here where it goes up like that, or it can come down the other side like this, and we're never below the line, okay? And so because of that, we know that they're always going to have the same domain, the same x values, because they're always going to have an infinite amount of x's. They're always going to have the same range because they're always going to be above the x-axis, so they're going to be positive y's. And then an asymptote, let me show you as a reminder. An asymptote is a line that continually approaches a given curve but does not meet at any finite distance. And our exponential functions are always going to have that same asymptote. So you can see here, these are images of asymptotes where they have a separate line, but a exponential equation or function always has an asymptote that is 0 or close to 0, right? It's always almost approaching 0, or the x-intercept. So we know that they're going to have the same of those three. Our next problem has to do with geometric sequences, which means that we need to go back and remind ourselves what are the formulas for geometric sequences. So we're going to take a minute and write those down. All right, so an explicit formula here, geometric sequence. Where'd my pen go? There we go. Recursive looks like this. So we have a sub n equals r times the quantity a sub n minus 1. A sub n minus 1 is our previous term. A sub n is any term in our sequence, and r is representing the rate or ratio that we are looking at this pattern. So remember, sequences are like sequences of numbers. Geometric sequences have to do with multiplication or division. Explicit is a sub n is equal to a1. A1 is representing the first term in our sequence with our rate or ratio in parentheses, and then our exponent becomes the previous term. Okay, so if I take this explicit formula here and I rearrange it into a recursive one, I am taking this rate is 1/5, so that becomes outside the parentheses. 125 is my first term, so when we have recursive, you write the first term as a separate kind of equation over here, whereas in explicit, the first term is included in it. So 125 comes out here, and then my a sub 1, or my a and my n minus 1, my previous term, goes in the parentheses. All right, number 13 is actually similar to is exactly the same as our warm-up the other day, where we have our exponents. So as a reminder, our bases need to be the same. If they are not the same, we need to rewrite them as the same. So I have it all kind of written out over here, but I'm going to kind of re-explain it a bit over on the left. I know that 1/3 squared is the same as 1/9 because I end up doing 1 squared over 3 squared. And that's how I get 1/9. So basically I rewrote here 1 to the 9th as 1/9 as 1/3 squared. When that happened, the square is now being multiplied to the whatever the power was originally, and that is due to one of our properties of exponents. And so now that my bases are the same, I can get rid of the base, and my problem is x plus 1 equals 2 times the quantity x plus 3. Then I solved over here on the left, and I got -5. Okay. 14, we're doing the same type of idea. The difference here is that we've got a division problem. So I'm going to write this. I'm going to change colors so you can see it better. I'm going to write this a little different. So I have 3 to the power of x to the power of 1/2 over 3 to the power of 1/2. And that is 3. Remember, any whole number has an exponent of 1. Okay, because this is a power of a power, we're basically going to multiply each other. So we're going to have 3 to the power of 1/2 times x divided by 3 to the power of 1/2, and that equals 3 over 1. When I divide exponents, I subtract them. So I'm really going to have 3 1/2 x minus 1/2 equals 3 to the first. Now I'm to a point where both of my bases are the same. So I'm going to get rid of them, and I'm left with 1/2 x minus 1/2 equals 1. Add the half to the other side, and I get 1/2 x equals 1.5, or 3/2, times both sides by 1/2, or the reciprocal, divide both sides by 1/2, and you end up with 5 halves. No. 3 times 2 is 6. 6 halves, which is 3. And that's how we got an answer of 3. So it's a lot of work there. And some of these steps you could have skipped if you knew what you were doing, but I wanted to write them out so you can see how I got there. Number 15, we have another geometric sequence problem. I am given the recursive, and I need to write the explicit. So again, in my explicit, I have it over here on the left. So I have to take A1, plug it in here. My rate, which is found in front here, goes inside my parentheses. And then I have n minus 1. So that's how we get B. Okay, another thing you might have to go back and remind yourself about is 16. It has to do with geometric sequences again, except that this time we're dealing with the formula. You still have A1, your original term. I believe it's the explicit one. You have your rate inside, except that it's going to be 1, because this question is dealing with growth of change or decrease of rates, right? Growth and decrease. So it's either 1, and it's either plus or minus the rate, and that is raised to the power of your previous term. Okay. In this case, Leo is investing $2,000. That's my original amount. I am earning in money, so I am increasing my rate of 4%. So I'm writing that as a decimal. It's compounded annually, so I'm just doing it this one time. And I want to know how much it's at the end of 3 years. So in this one, actually, I don't think it's the n minus 1 that we write for this guy. It's basically, it's time in the corner. I don't remember what we use there, but basically you're going to take that time here, that 3, and that's going to become your exponent. And then you just plug it into a calculator. So if I plug in the 1.04 raised to the power of 3 times 2,000, I get 2249.73. Done. Easy as that. Okay, number 17, we have this function right here on our paper. It's an exponential function, and we need to figure out which of these equations is correct. So remember, all of them are going to have that same asymptote. And in this case, we're going to have this y-intercept pretty much be the same, because if it's one of these basic exponents, anything to the power of 0 is 1. So it doesn't matter what your base is. Anything to the power of 0 is 1. So therefore, all of these equations have the same y-intercept. But the one number that we can solve for that is going to be different will be if x is 1. This point right here will be different for each of these graphs, each of these equations. So 1 to the power of 1 is 1. 3 to the power of 1 is 3, and 6 to the power of 1 is 6. So because my answer, when x is 1, my y value is 6, C is the correct answer. And then below on 18, we're going back into that population equation. So I'm taking my original amount. This is the same as number 16. I am timesing it by 1, we're growing, plus a rate of 4%. And I want to know what it'll be in 6 years. And I'm just going to plug that into the equation, and that's how you get C. Or sorry, plug this into a calculator, and that's how you get C. Now on number 19, our answer is 6, and the way I get that is kind of a guess and check. I basically, again, I'm going to have that same equation from the last problem, but this time I know my y, I know my answer, I know where I start at, right? I know that I'm decreasing by 8%, but what I don't know, I'll move this down, but what I don't know is the variable here, how long this is going on. And so what I have to kind of do is kind of say, okay, well, what if it was 4 years? What if it was 5 years? And plug it into my calculator. The other thing is I don't want these to actually equal 11,000. It wants it to, in how many years will the population be fewer than 11,000? So I want to know, when is the right side of my equation going to be less than my left side of my equation? So I would do kind of a guess and check, and I would start, kind of high, like 2 or 3. I probably wouldn't just, 1 isn't going to help, but maybe we start at 3 or 4, plug it into the calculator, and try to solve for this x right here. Okay, it's kind of like a guess and check in this case. But once you get to 6, and I'll show you, once I get to 6, so if I do 1 take away 0.08, that raised to the power of 5, we'll do this one first, times the 18,000, I'm at 11,863. Now, if I do 1 take away the 8%, raised to the power of 6 times the 18,000, I am now under 11,000 into 10,000, and that's why it's 6. Okay, the very last one here is adding 2 of these polynomials. So when I'm adding, I'll kind of show you, let me lay it out and then I'll show you what I'm doing. Okay, so what I went through was I identified the like terms in both equations, and because I'm adding both, I don't have to worry about signs changing. If I was subtracting, I'd have to kind of distribute that negative or minus. But in this case, I'm just going to add them together. So keeping the sign that's in front, I found like terms. Excuse me. So I had my x cubed here. So 5x cubed plus 2x cubed is 7x cubed. Okay. Automatically, I know it's not C or D. Then I'm going to subtract 5x squared because there's no other x squares. And now already I know that it's A. But if I wanted to continue and make sure, I would then do plus 7x take away x, so that's plus 6x, and then minus 8 plus 3 is minus 5. And there we go. That is A. Good luck to you. Let me know if you have any questions in class, and we'll start working on the next 10 soon.